Hey ChemStars, this is Mrs. Vanderlei bringing you another ChemStar video. We are still in chapter 5, but we'll finish it today. We are in section 5.3, which is the periodic trends or the periodic properties. And today we're going to talk about electron affinity and electronegativity, and then we're going to summarize everything, okay? So let's talk first about electron affinity. What does this word affinity mean? It means love of, loving. All right, so I could say I have a chocolate affinity. What does that mean? I love chocolate. Okay, so if one of my kind students comes and brings me a big box of chocolate, all right, what do you think I'm going to do when I receive this big box of chocolate from one of my students? I'm going to do this. Whoopee! Oh, hallelujah! I love chocolate. This is awesome. Thank you so much. Yep, I'll do that. All right. So what if I don't like, oh, I don't know, sardines? All right. So what if one of my students who's trying to be kind to me brings me a box of sardines? Well, thank you. I really appreciate the gesture. Thank you. What am I going to say? Am I excited? No. So what am I trying to get you to see here? So what is electron affinity? It's the energy released when an atom gains an electron. So for Mrs. Vanderwally, that was the yippee I released when I gained the chocolate. Okay, so an atom can gain energy, I'm sorry, will release energy when they gain an electron. And they will do that if it's beneficial, if it's going to help that atom become more stable. So it's all about filling its orbitals, okay? So how is this related to attraction? Well, the greater the attraction, the more energy released. So the electrons that become, or excuse me, the atoms that become the most stable when they gain electron, it's going to release the most energy, all right? So as you go across the period, what do you think is going to happen? Electron affinity is going to increase. However, the noble gases have very low electron affinity. Why is that? They already have a filled shell, filled p shell, I should say. They don't need any more electrons to become more stable. They're already as stable as can be, okay? So what happens as you go down a group? You decrease. So what I have here is the trend for electron affinity. Again, as you go across the period, you're going to have more protons, so you're going to have greater attraction for the electron. As you go up here, so you have fewer shells, they're going to be closer to the nucleus, so you have greater attraction for those protons. But notice what I did here, and I recommend you doing the same thing. Your noble gases are already stable. They already have a filled p shell. They have a completely filled energy shell. All right, they don't want another electron to become more stable. If anything, it'll become less stable. So which element then is in the upper right-hand corner if we omit the noble gases? Well, it's fluorine. So which element is going to release the most amount of energy? Woohoo! Whippy! It's fluorine. Okay, so which is my sardine receiver, if you will? All right, well, it's the opposite. That's your francium. Oh, thanks. Okay, actually, francium's to the point where it will not release energy, but you have to force energy to it to gain another one. So it's not releasing. You have to add energy to francium to make it receive it. So that's kind of not really helping out, is it? So let's go through these. So which of these have a greater electron affinity? So lithium or fluorine? I sure hope that's a no-brainer. All right, which one would I make a big deal about? It is definitely fluorine. Why? It has more protons. It's in the same period, right? More attraction. It needs that extra electron to have a filled 2p shell. That'd be awesome. Okay. So what about fluorine or iodine? Well, duh, fluorine has the greatest. Okay, well, it has fewer shells, more attraction. Keep this in mind. Iodine can also receive one more electron to have a filled shell to be like a noble gas. But fluorine is closer, or the outer electrons are closer to fluorine's nucleus, so it has even more attraction, okay? So what about lanthanum Or what am I doing? Sulfur. Sulfur is actually being hidden here. Sulfur is right here. So which one is it? Well, it's at diagonal again. So hopefully it is sulfur. You have fewer shells, more attraction. And then what about this last one? Vanadium or helium? Here's vanadium and here's helium. Well, which one are you going to pick? Hopefully you're going to pick vanadium. All right. Why? It's not a noble gas. Don't ever pick the noble gas. All right. That's not a good idea. So what I'd like you to do is to pause this. I mean, pause it. Fill out the next, I think it's 5. All right. And then when you are done, come back. Did you pause it? Okay, welcome back. Let's see here. So zirconium or tin, they're both in the same period. So which one has a greater electron affinity? Tin. All right, chlorine or sulfur? Well, they're in the same period. Here's chlorine, here's sulfur. They're in the same period. Well, which one is it? It is chlorine. Has more protons, more attraction. What about lead and carbon? Here's lead, here's carbon. It's going to be carbon. Why? Fewer shells, more attraction. Well, bromine or fluorine? I sure hope that's a no-brainer. It's fluorine, okay? Fewer shells, more attraction. All right, what about nitrogen or boron? They're kind of almost next to each other, aren't they? Here they are. All right, so nitrogen has what? More protons, more attraction. Do you see how it is the same answer for all of these? It's all about attraction, isn't it? So this next section is about electronegativity, and it's very, very similar to electron affinity. So let's see what it's all about. Let's go to the next page. So what is electronegativity? Electronegativity is the measure of the attraction for an electron in a bond. I call it a tug of war. So what happened is that a guy named Linus Pauling got a little bit, tired of dealing with electron affinity and measuring the energy being released and trying to figure out which element has the biggest yippee. All right, so what he did is he decided to rank them. All right, and knowing that fluorine has the highest electron affinity, he said, well, this was going to have the highest electronegativity. And I'm going to base every other element based on fluorine, okay? And he gave fluorine a 4.0. That's going to be the most electronegative element there is. And somebody asked him, why did you pick 4.0? If you're going to like rank them, why don't you make it a 10, like a perfect 10? And he said, oh, that's my golf handicap. So we can thank Linus Pauling for being a pretty good golfer and make now the fluorine being your 4.0. So now he's going to compare like the bonds, I'll say fluorine and oxygen. Where are the electrons? Well, they're closer to fluorine because fluorine has a bigger electronegativity. All right, so what about fluorine and, I don't know, hydrogen? All right, so look at that. Well, the electrons are going to be a lot closer to the fluorine than the hydrogen because there's a bigger difference in their electronegativities. All right, so that's that idea of tug of war. So those electrons are physically closer to the fluorine because they have a greater attraction for those electrons than the hydrogen does. Okay, so you can look at these numbers, say, okay, where in the bond? So if I have a bond between carbon and nitrogen, where are those electrons? They're going to be closer to the nitrogen. Okay, so as I go across a period, what's happening to electronegativity? Well, here's lithium, beryllium, boron. I think we can see they're all going up, aren't they? So as you go across each period, yes, they're going up, all right? So as you go down the group, what's happening? 2.1, 1.0, 0.9, 0.8, they're going down, aren't they? All right. So what do you notice here? Look at the next question. Actually, this is a really important question, okay? The electronegativity of nonmetals are what? Bigger or smaller than the metals? All right. Well, you know what we ought to do first? Let's go ahead and make something real quick, all right? So I'm going to put, why don't you do this too? This is the line between the metals and the nonmetals. You remember that? So there's metalloids that are on the line. Okay, but here are my nonmetals, right? And here are my metals. So which one? The electronegativity of nonmetals are what? Well, look at these numbers. They're like in the 2s and the 3s and the 4s. These are all in the like points and the 1 points. All right, so I think you can easily see that these are the bigger numbers, and that's super duper important. Now, Mrs. Vanderwall, you won't see this in a textbook anywhere. have a name for these. What do you notice about those? I call them the big four. Why do you think I call them the big four? They're the four largest electronegative values. Okay, and that's a big deal. It really is. So we're going to come back in chapter 6 and we're going to revisit this idea of the big four. Okay, and before we go on, I just want to tell you one more thing. The periodic table that you have a lot of, you know, the full-size sheet of paper that you probably have like 10 copies of, they all have also the electronegativity values on it. So if you pull it out and take a look at it, you'll see your fluorine. And you'll see that it has a 4.0 in that chart there too in the periodic table. So you can look up every element. And if you'll do that, you're actually going to notice something, that your noble gases, your helium and your neon actually have dashes. There is no registered value because it can't, it will not bond. But the larger atomic radius, larger noble gases, actually does have values for electronegativity, all right? So things get a little bit wonky when you talk about how large those are. And they, you know, but just know that the current trend is still correct, okay? All right, so let's keep going. So which one has a greater electronegativity? I didn't put those arrows here again. It's the same arrows as before. Cross out your noble gases. Fluorine is your biggest, francium is your smallest, just like electron affinity, okay? So which one has a greater electronegativity, beryllium or oxygen? Well, two things, they're in the same period. So which one has more protons? Oxygen does. What else? Write this down. Oxygen's a non-metal. Beryllium's a metal. Always pick your non-metal over your metal. So what about beryllium and barium? They're both metals, but they're in the same period, or excuse me, they're in the same group, aren't they? So which one's going to have the greater electronegativity? The one that's higher up, all right? So that would be beryllium. How about fluorine or radon over here? Well, folks, I hope that's a no-brainer. It better be fluorine because fluorine's the biggest of all, okay? Also, what else you notice? Fluorine's the non-metal. Radium's a metal. Always pick your non-metal. So which four elements? Mrs. Vanderlei calls them the big four. So what are they? Here they are. So what I would like you to do next is to pause this and answer the next like 5 questions, all right, about electronegativity, okay? And you notice it's the same pattern over and over again. So pause this, and I mean it, and when you're done, come back. I hope you paused it. Okie dokies, welcome back. So the first one is your carbon or your boron. They're side by side. It is carbon. Why? Has more protons. It's closer to fluorine, isn't it? All right, what about chromium, which is here, and bromine? They're in the same period, aren't they? All right, well, bromine is. Why? Well, it has more protons, but what did I write? Always pick the non-metal over your metal, okay? Now, what about gold and copper? Gold and copper are both metals. So here's copper, here's gold. Pick copper, it's higher up. All right, fewer shells, more attraction. What about lead and cesium? Here's cesium, way over here is lead. Pick the lead, it's closer to fluorine. It has more protons, more attraction, higher electronegativity. And then I'm hoping that number 5 was a no-brainer. Why? Because fluorine wins out over everything. Okay, so the next page is a summary of everything that we've talked about. Okay, so let's go there. So this is a summary of trends, and poor electronegativity got kind of didn't get included. So I put electronegativity underneath where it says electron affinity. So as you notice, this upper right-hand corner is a hotbed of activity, okay, of electron affinity, of electronegativity, of ionization energy. And really, the only trend that comes down here is the radius. So francium is the biggest element, but the smallest of everything else. And now we have two new terms here. What's a non-metal character? Well, if it's more non-metal, it has a greater ability to attract electrons. And does that make sense? All right. If you're going to attract electrons, that means you have a high electron affinity. You have a high electronegativity. So you have great love of electrons. What else does that mean? You have a very high ionization energy. You don't want to get rid of electrons. You want to gain electrons. So yeah, it takes a lot of energy to remove an electron from a non-metal. All right, so what about a metallic character? The more metallic is the greater ability to lose electrons, all right? So it has a very low ionization energy. It has a very low electron affinity. It doesn't want to gain electrons, it wants to lose them. All right, so this should all make sense. And again, the atomic radius also goes in this corner. So everything put together, finally, why are we learning this? So we can learn about chemical reactivity. And we will come back and revisit this in chapter 8. Don't worry, all right? But why care? Well, the metals that are the most reactive will lose electrons the easiest. Why do I care? Well, look in your pocket. Do you want your coins to react pretty easily? You're going to lose your coins. Do you want those metals in your cell phones that you highly value to disintegrate because they reacted? No, you don't. All right, so it is so important when planning out what materials you should use to make something that you don't want it to react, or maybe you do want it to react, okay? So this is a really important thing in industry when you're making things, all right? What's going to react, what's not going to react, okay? So the metals that are the most reactive will lose in the most, has low attraction, low ionization energy, low electron affinity, and low electron activity. So which are your most reactive groups, all right, is actually group 1. Do you remember that video when the bald guy with the British accent, when we were talking about the periodic table, he was throwing lithium in water. He was throwing sodium in water. He was throwing potassium in water. Right? And what happened when he threw it in water? It blew up. It caused a fire. Now, aren't you glad if your nickel gets wet, it doesn't blow up in your pocket? That would be bad, all right? But the alkali metals do, all right? That's your group 1. Does that make sense? Francium, we said, was like the most everything or the least everything in that respect, all right? The least electron loving, the least electronegative, the one that has the lowest ionization energy. Why? Because it will lose electrons the most. Well, then which one? That's your group 2, the alkaline earths. Do you remember that metal non-metal lab? Do you remember that letter B of the metal non-metal lab? You put the water on it and it fizzed and it bubbled and it got hot. It was really fun to do and I got all excited. Remember that? That was actually calcium. All right, letter B was calcium. Here's where calcium is right here. That's your group 2. All right, which reacted more. Okay, then what? Well, then most of your transition metals, all right? So your D block, some of your P block, actually your F block, all right? They're kind of generally in the same relative category. They don't blow up in water. They don't fizz and bubble really easily in water. It's not something like, ooh, look at that, okay? But then we have 3, I call the precious, okay? So if you're a Lord of the Rings fan, you probably know what I'm talking about. So precious, your gold, silver, and platinum. All right, so will they react? Not at all. So why do you think your early coins were gold and silver? Because they didn't react. If it rained on them, nothing happened. Even copper tarnishes. Even copper might turn green, but these folks don't. Okay, they don't react. So they're your precious metals and they're the least reactive. So what about your non-metals? You want those to be high attraction, high ionization energy, high electron affinity, high electron activity. They are going to gain the electrons the easiest. So take a wild stab. Which group is going to do that? Well, which one was the focus on the last 2 trends? All right, wasn't that fluorine? All right, well, what group is fluorine in? Fluorine is in the halogen group, aren't they? All right, that's your most reactive groups. All right, hey, which one smelled the worst? Halogens. All right, they're the most reactive group. And actually then group 16, the oxygen family. And does that surprise you? Well, what's your second most electronegative element? Oxygen. All right. And then after that, your group 15, that's your nitrogen family. Does that surprise you? Probably not, because remember how nitrogen was tied with chlorine, which is already in this group for electronegativity? Probably not. Has carbon been mentioned much at all? No, it's not very reactive. Now, you can burn carbon, okay, but you need to have that little spark in order to do that, okay? These others are a little bit more reactive. Finally, which is your least reactive groups? your noble gases. Okay, well, that concludes your Chapter 5 videos. Don't wait to be great. We'll see you next time. Bye-bye.